A nuclear bomb could destroy a city, a large asteroid could devastate Earth, and a nearby supernova could sterilize much of a solar system. But none of those things would destroy the universe. Even the largest explosion imaginable would still happen inside the universe, while space and the laws of physics continued around it. To erase everything, you would need something stranger than destruction. You would need to change the invisible rules that allow particles, atoms, stars, and people to exist. Physics has a name for one hypothetical process capable of doing that: vacuum decay. It would not merely blow up the universe. It could rewrite what the universe is. To understand vacuum decay, forget the everyday meaning of the word vacuum. In physics, a vacuum is not simply an empty box with everything removed. Invisible quantum fields extend through all of space. What we call particles can be understood as excitations, small disturbances inside those fields. One example is the Higgs field. It exists throughout the universe, and elementary particles interacting with it acquire properties including mass. You, the desk, and the planet beneath it exist in their familiar forms because these fields currently have particular values. If those values changed, matter might behave very differently. Imagine a ball resting inside a shallow valley. It appears stable. Unless something disturbs it, the ball could remain there for an extremely long time. But this shallow valley is not the lowest possible position. Beyond a tall barrier, a second and much deeper valley exists. A state that is stable for now, but not at the lowest possible energy, is called metastable. In this analogy, the shallow valley is a false vacuum. Our universe might occupy a similar state. That does not prove it is unstable. It only means that, under some calculations, a lower energy arrangement of the fields may exist. In normal life, the ball could reach the deeper valley only by gaining enough energy to cross the ridge. Quantum mechanics permits another possibility. At microscopic scales, a system can sometimes pass through a barrier instead of traveling over it. This is quantum tunneling. If our vacuum is metastable, an extremely unlikely quantum event could theoretically move one microscopic region of space into the lower energy state. A bubble of true vacuum would appear. If it were too small, it would collapse immediately. But if it exceeded a critical size, it could begin to grow. The bubble's boundary would cost energy to maintain. That boundary would try to pull inward, much like the surface tension of a soap bubble. At the same time, the lower energy interior would favor expansion. Below the critical size, the wall wins and the bubble disappears. Above the critical size, the balance reverses. Expansion wins. The bubble releases more energy by growing than it requires to enlarge its wall. Under the catastrophic scenario, the wall would accelerate toward the speed of light. A microscopic quantum event could become a growing region that no ordinary force could stop. This would not resemble a normal explosion. There might be no fireball, blast wave, or cloud of shattered planets. The wall would replace the existing configuration of quantum fields with a different one. The region behind it might obey unfamiliar physical rules. If fields such as the Higgs field settled at different values, elementary particles could acquire different properties. Their masses and interactions might no longer match those in our universe. Atoms might become impossible. Chemistry might cease to function. Or matter could transform into something no human theory currently describes. We cannot know the exact result without knowing the true vacuum. Suppose such a bubble formed somewhere in space and its wall accelerated to almost light speed. Could astronomers detect it and warn us? Probably not. To see an approaching object, like carrying information about it, must reach us before the object itself. But a relativistic bubble wall would travel nearly alongside any warning light. There might be no useful signal arriving ahead of it. the sky could look normal until the final instant. There would be no evacuation, no shelter, and no last message. The boundary would arrive before anyone understood that it existed. When the Large Hadron Collider began operating, some people feared that violent particle collisions might trigger vacuum decay. The concern sounds reasonable at first. The LHC accelerates protons or ions to almost the speed of light and collides them inside enormous detectors. But nature has conducted higher energy cosmic ray collisions for billions of years. They have struck Earth, the Sun, white dwarfs, and neutron stars without producing an observed expanding vacuum bubble. If ordinary high-energy collisions easily destroyed the vacuum, natural collisions would probably have done it long before humans existed. The continued survival of ancient astronomical bodies is powerful evidence that the LHC is safe. The disturbing part is that vacuum instability is not merely an idea invented for science fiction. Measurements of the Higgs boson and top quark allow physicists to investigate the stability of the Higgs field. The Higgs boson has a measured mass of roughly 125 billion electron volts. Using current central measurements, many standard model calculations place our vacuum in a metastable region. That conclusion is not final. It depends heavily on extremely precise measurements and on whether unknown physics exists beyond the standard model. And even when calculations favor metastability, the expected lifetime can be vastly longer than the universe has already existed. Metastable does not mean about to collapse. So, how do you destroy the universe? The honest answer is that we do not know how. No proven machine, collision, or experiment can create a destructive true vacuum bubble. We do not know whether a lower vacuum truly exists. We do not know whether undiscovered particles or forces stabilize the universe. And we have no evidence that human technology can trigger such a transition. But the possibility teaches us something profound. Reality may depend on invisible fields remaining in the configuration they occupy today. If vacuum decay were possible, the universe would not end by exploding. It would end by becoming something else. The universe may have a delete button, but according to proven science, nobody knows where it is. Nobody knows how to press it, and nobody knows whether it exists at all.